Hello, thank you for joining me in this presentation. My name is Stefan Alecu, and I'm here to present my research work on the topic of expressive brass wind modeling, which was supported by the Nordic SMC network and by Audio Modeling, a software development company based in Italy specialized in production of virtual expressive acoustic musical instruments. This project, titled Embouchure Interaction Model for Brass Instruments, was done together with Stefania Serafin and Silvin Willemsen from Aalborg University Copenhagen, and with Emanuele Parravicini and Stefano Lucato from Audio Modeling. In 1973, John Chowning, one of the leading developers at Stanford University, innovated the technique of emulating complex audio spectra using frequency modulation synthesis. One of the benchmarks for testing the quality of this synthesis method was to emulate brass-like tones. Before and since then, emulating brass sound has been considered one of the more difficult benchmarks for audio synthesis testing, especially in the field of physical modeling. This is due to the human factor, which plays an important role in shaping the sound of the brass instrument. More exactly, it's because of the nonlinear characteristics of the brass player's lips and mouth muscles, which form the embouchure component of the instrument. While many state-of-the-art approaches in brass wind physical modeling have pushed the quality of the timbre to a higher level, its potential as an actual instrument for expressive sound synthesis is still far from being achieved. With the advent of hardware platforms that encourage expressive interaction with virtual instruments, like the Rolly Seaboard, there's a need in designing physical models with expressive control. This means that details lost to oversimplification of the interaction with these models need to be recaptured in some capacity. Thus, the focus of this project is on modeling the embouchure of the brass wind instrument by taking the simplified state-of-the-art approach and adapting it to consider the influence of additional aerodynamic forces. The sound of a brass instrument is generated from the airflow that passes through the brass tube resonator, which is modulated by the vibrating lips of the player. This interaction between the lip reed and the air tube is simplified by considering the lip reed as a mass spring system coupled to the tube resonator. As the airflow moves underneath the mass spring, the system is put into motion by the pressure forces arriving from the player's mouth, denoted by PM, and the pressure within the mouthpiece, denoted by P, which also includes the reflected pressure waves from the tube resonator. As the mass spring is moving up and down, it shapes the flow underneath it and varies the pressure within the reed channel and the mouthpiece. The mass spring starts vibrating considerably when the resonance frequency of the system is nearby one of the tube's natural frequencies. However, if we remove the tube from the system, the mass spring ceases to oscillate. In real life, though, the lips can still move and even vibrate from the interaction with the airflow generated by the mouth. Thus, we need to consider that self-oscillation of the system is possible and can be maintained by the airflow. This phenomenon is known as vortex-induced vibration, and an example of such an occurrence is the vibration of bridges or structures due to strong wind. Consider an object placed within a traveling flow. As the flow moves across the object, instabilities are formed in the layer around it. From these instabilities, alternating flow vortices on opposite sides are formed, which change the pressure distribution along the object's surface. This change in pressure distribution creates an alternating lift force, which puts the object into motion. The state-of-the-art approach in physically modeling the lip reed uses this mass spring presumption. Mathematically, the unknown variables within this interaction system are the displacement of the reed spring, the pressure within the mouthpiece channel, and the volume flow rate underneath the lip reed. These are derived from equations that describe the entire interaction, such as the forced harmonic oscillation of the mass spring and Bernoulli principle applied across the reed channel. From other previous works, the following mechanical details are also implemented in the model, including lip closing emulation, which is achieved by increasing the rigidity of the lip reed during collision, or the control of the resonant frequency of the mass spring through mass and elasticity adjustments. The innovative contribution to the model comes in the form of the Viv lift force added to the mass spring model. Consider the following mass spring object added within a traveling flow, and the following equation of a forced harmonic oscillation where the excitation force is the lift force, Lt. This lift force can be simplified as a velocity component to the harmonic oscillator, which varies the spring's damping coefficient. The lift force component is considered inversely proportional to the lip displacement. There is no exact formula to determine the proportions between the displacement and the lift force, so an empirical relation is derived, which would assure self-oscillation of the mass spring. A final detail is the addition of noise modulation for mouth-blowing pressure parameter PM. The pulse noise signal is used as a modulation function, which consists of a wide Gaussian noise passed through a bandpass and high-pass filter. The mean blowing pressure amount, PM0, is modulated based on the derived noise amount and the normalized lip displacement. The cutoff frequency of the high-pass filter is dependent on the reed aperture size. The presented model has been implemented as a real-time VST plugin, for which I will give now a short demonstration. Okay, now the VST plugin is loaded up. As we can see, the model can seem a bit intimidating with the sheer number of parameters available, but for interacting with the model itself, we only need to use 4 parameters, which are the lip resonant frequency, the tube resonant frequency, the blowing pressure amount, and the tube feedback, which is a feedback constant that controls the amount of reflected pressure that are being applied from the tube resonator towards the lip reed model. At this tube feedback value, the model is being affected both by the reflected pressure waves from the tube resonator and by the empirical lift force for the vortex-induced vibration. So now let's first start interacting with the model using only the lip resonant frequency. We increase the blowing pressure towards a high enough value, and then we can start interacting. So as we've heard, the sound of the model is pretty spot on. It's a pretty realistic sound of a brass instrument. Towards the higher frequencies there are some noticeable artifacts, but all in all it's of a good enough quality. It allows us to have a more continuous and expressive interaction with the model itself, possibly supporting a playing style like legato. Now, if we take this tube feedback and try to decrease it towards -1, we're basically increasing the amplitude of the reflected forces from the tube resonator, and we're subduing the influence of the lift force from the vortex-induced vibration. In this situation, we've observed that the model generates a much clearer sound, but the transience between the harmonics is almost non-existent and kind of limits the actual frequency range of playing for the system itself. Now, if we set the tube feedback to 0, we're basically removing the tube resonator from the lip reed model, and the model can vibrate by itself due to the lift force. Now, to achieve self-oscillation in this case, you need to strike a fine balance between the blowing pressure amount and the lip resonant frequency, because the model is pretty unstable in this situation. Okay, now we're gonna interact with the tube resonance frequency, In this case, we're basically controlling the length of the tube resonator. First, we're going to do some small changes to simulate the slide effect, and then we're going to do larger and larger changes. Finally, we're going to simulate the breath noise modulation capability. For this model, I've also implemented a MIDI mapping interface. The MIDI node frequency controls the lip resonant frequency and the tube resonant frequency. The MIDI modulation value and pitch bend control only the lip resonant frequency, while the tube resonance remains the same. The note velocity defines an initial amount of blowing pressure, and expression parameters like a MIDI expression pedal or the aftertouch feature of a MIDI keyboard can also add more blowing pressure to create a more natural envelope of the sound. Now, unfortunately, for this demonstration, I don't have a MIDI keyboard with an expression pedal or an aftertouch feature. Instead, I'm going to use an unassigned MIDI knob that can control the additional blowing pressure amount. As we have heard, the model is able to synthesize sound whose timbre is strongly similar to that of a general brass instrument. Another indication by how close we are to the real behavior of the model is through signal comparison. On the left side we have plots for the synthesized pressure signal. The figure A shows a pressure signal without noise modulation, and figure B shows with noise modulation. And on the right side we have, from a previous research, real-life measurements of pressure within the mouthpiece channel. The influence of VIV is remarkable, since it controls how audible the transients are between the harmonics of the tube, extending the available frequency range of playing. A shortcoming of the model is the difference between the lip resonant frequency set by the user, denoted by FL, and the measured fundamental frequency of the lip vibration, denoted by Fout, as we can see in this table of data. The difference is caused by the lip collision effects, which modify the rigidity of the mass spring, which in turn also changes the resonant frequency. Additionally, behavioral errors are also present in the model, which are due to the empirical design of the lift force and some other aspects of the implementation. An example of this would be the inaccurate dynamic behavior. As we increase in blowing pressure PM, we would expect an increase in higher frequency harmonic energy, but this is not the case for this model. That being said, the developed VST plugin shows the potential of this Embouchure prototype. The influence of additional aerodynamic forces show how the available frequency range is extended, which aids the expressive capability of the Embouchure model. We've shown that the model supports more expressive playing styles like legatos and slides. The model can be improved certainly in many aspects. Two main topics of focus could be the redesign of the lip model to improve VIV interaction and a more realistic tube implementation. Thank you for watching. If there are any questions, I will be more than happy to answer them.
Hello, my name is Silvin Willemsen, and today I'll be presenting for you our paper titled Real-Time Implementation of a Physical Model of the Tromba Marina. So first I'll go into what a tromba marina is, then I'll describe in detail the physical models that we use to simulate the instrument, and then I'll give some details on the implementation and end the presentation with a demo of the application. So first of all, what is a tromba marina? I'll show you a brief sound snippet so you can listen to it, actually. So as you can hear, it's kind of like this, it has a brassy timbre, or a timbre of a trumpet, but actually it is a bowstring instrument from the Middle Ages with a rattling bridge, or a shoe, due to its shape. So the string rests on this bridge and rattles it against the body as it is bowed, creating this brassy-like timbre, which is quite interesting. So the way that the instrument is played is by slightly damping the string at different locations using a finger or a knuckle, and these locations should be half the string, a third of the string, a fourth of the string, etc., to induce harmonics, and then it is bowed above the finger as opposed to what you would expect from a bowstring instrument such as a violin or a cello. So I'll quickly show you a video of me trying to play the tromba marina, which we had at the university, and trying to recreate the sound snippet that you just heard. So yeah, this is the way that it is played. So how did we go about simulating this? So we divided the entire tromba marina into three components. A string, which is a 1D system, the bridge we modeled as a 0D or point mass, and the body we modeled as a two-dimensional plate. So normally you use partial differential equations to describe motion of certain objects, and we describe them also in the paper in the form LQ equals 0, where L is a partial differential operator applied to a state Q, and this Q can be the state of the string, the bridge, or the body, and Q is defined over a domain X, which also depends on the system at hand. So for example, it will be one-dimensional in the case of the string and two-dimensional in the case of the body, for example, as we will see soon. And yeah, so let's go into the string. We have an operator now L subscript S for string, and a state U, which is defined over space chi and time t. And the operator looks like this, where this partial t and partial chi operators, they denote a derivative with respect to space, or time and space respectively. And then we have a list of parameters that describe the string, or the material of the string, where we have the material density, cross-sectional area of the string, etc., etc., etc. So this operator looks kind of scary, probably, for most of you. So let's just quickly go through what all these terms mean. So basically the acceleration of the string is dependent on a term that describes tension, a term that describes stiffness, and two terms that describe the damping as the string goes over time. Yeah, so that is the way that this operator is applied to the state U of the string. And then further on we will continue with this very brief notation of the form you can see in the top right, to have Ls of U, or applied to U, equals 0. Then we have the bridge modeled as a mass. So now we have a state variable W that is only dependent on time rather than being distributed in space. And the operator looks like this. So we have some tunable parameters, such as the mass of the bridge, the angular frequency of oscillation, and the damping. And again, we will use the shorthand notation to describe the movement of this string, or the mass. So now we have the body, where now we have a state Z that is described over two spatial dimensions, x and y, and over time t. And the operator looks like this, where now we have a derivative in two spatial dimensions, which is denoted by this delta, or 2D Laplacian operator. That's actually a second order derivative in two spatial dimensions. And then we again have some parameters by which we can tune the body. And then we end up with this shorthand notation again. So now we have three individual components: the string, the bridge, and the body, which are all equal to 0. So this means that individually they will work, but they are not interacting with each other. They are not connected. So we'll now go into the interactions between these components. So here you see a diagram of the bridge from the top, and our two main areas of interest are the bridge-body interaction and the string-bridge interaction. So we assumed that a horizontal movement of the string, the action it has on the bridge translates directly into a vertical movement at the body of the bridge, so that we can kind of stack all these components on top of each other rather than concerning this extra dimension. So let's look at the bridge-body interaction. So we modeled this as a collision, and the way we did this was to add a potential to the equations, where here our independent variable is eta, which basically describes the difference between the body at location xmp for mass plate and ymp, so the location where the bridge hits the body, and the bridge itself. So yeah, that difference is eta, and we have a operator, the subplus operator, which describes the positive part of. So you can see that if the bridge is below the body, eta will be positive, and there will be some potential that will create this collision effect. And then again we have two tunable parameters, which are the collision stiffness and nonlinear collision coefficient, to tune this collision potential. So then we can add to the partial differential equations the derivative of this potential, which I'll refer to as the collision term. And so the mass now has, or is equal to, this potential here, and the plate has at the location xmp ymp, which is denoted by this operator, which you can kind of see as a localizer. So it's a spatial direct delta function applied to this potential to localize the effect of the bridge onto the body. And also note that here we have the potential which has a positive effect on the bridge, and here it has a negative effect on the body. So you can see that a positive and negative effect is applied to the bridge and the body respectively. So if we discretize this or implement this, we need iterative solvers. But the authors of this paper, Ducceschi and Bilbao, in this context, propose to use a quadratic potential, so kind of rewriting this collision term a little differently, so that now we can add this to the partial differential equations, and now we can actually solve it explicitly. And I would like to refer you to their paper or the paper that I'm presenting now for more details on this. So moving on to the string-bridge interaction, rather than a collision, we model this as a connection. So the most important difference here is the use of absolute values rather than the subplus or one-sided operation, so that even if the difference between the mass and the string, in this case at string location chi sm, if that difference is negative, there will also be an effect, or there will also be a potential for collision. So in the same way, we can add this quadratic potential to both the string and the mass, and of course we need another spatial direct delta function to locate the bridge along the string, because we need a position for that. So to summarize, we started off with three individual components, which are the string, the bridge, and the plate. Then we took a look at the string bridge interaction by which we added the potentials, now with their respective subscripts, Sm for string mass. And this potential, or these collision terms, are dependent on the distance between the bridge and the mass, the bridge and the string at string location chi Sm. Then we have, we also added an other potential to the mass and a potential to the, or a collision term to the plate, where the distance between the bridge and the plate, eta mp, is influencing these collision terms, and the location on the plate, xmp, ymp, is what is taken into account here. Then the one thing that we're missing is the bow, so we actually need to interact with this system. And to do that, we can add an extra term to the string, which is this term. Again, we have a spatial direct delta function that localizes the bow on the string, and this is applied to a force and a nonlinear bowing function dependent on the relative velocity between the string and the bow. For more details, by the way, I would like to refer you to the paper. And lastly, we actually need a damping finger to induce the harmonics along the string. And we model this like this. Again, we need the spatial direct delta function, now at location chi of f. And so now we can actually play different pitches on the string. So for the real-time implementation, we discretize the entire system using finite difference time domain methods, but I won't go into details here, and I would like to refer you to the paper to show you how we did that. Then we use C++ and the JUICE framework to implement this in real time, and I think it's best if I show you a demo instead of talking about it. Alright, so this is the Sensol, and it is a device that contains about 20,000 pressure-sensitive sensors, with which it can detect X position, Y position, and Z position through pressure. So this is the application that we made. As you can see, we have here the string, the mass connected to the string or the bridge, and the body of the tromba marina. And here on the side we see the bridge and the body from the side. So we can interact with this setup by interacting with the Sensol. So we can see that the bow moves as I move my finger. And the pressure is linked to bow force, and the vertical velocity is mapped to the bow velocity. And the second finger with which we interact with the Sensol is mapped to a damping finger. So we can actually induce harmonics. And these lines that show up, they denote where the next harmonic should be. So as a guide to the player, where to place the finger to reach one of those harmonics. And interestingly, the higher up we go, the harder it is to play, just as with the real instrument, and the more pressure matters in order to actually get one of those harmonics. Both pressure in the finger and the bow. But yeah, so this is the application. We have 3 sliders here on the right, where we can change different volumes of the different components. So we can listen to the string only, like this. So we have the string, the body, and the string, the bridge, and the body as volume sliders here. So now we only listen to the string, so we lose the kind of rattling sound. We can also only listen to the bridge. Creates this, or we can only listen to the body. So only when there's a rattle, we can hear the body. Alright, so thank you very much for your attention. If you have any questions or are interested to know more, you can always send me an email through this address. And I hope you will have a nice virtual conference. Thanks.
Hello SMC 2020. This presentation is titled Insights into the String Barrier Interaction Dynamics based on high-speed camera measurements. My name is Dmitri Kartofelev. I'll be presenting this talk. In addition to me, this paper is co-authored by Joann Arro and Professor Vesa. We represent Tallinn University of Technology and Aalto University, respectively. In this talk, we'll present a time-stepping model for modeling collisions between a vibrating string and a rigid barrier, and compare this model against experimental measurements. This presentation is motivated by the fact that in guitar and other lutes, strings may collide against fretboards or other rigid objects, such as nuts, while played. The outline of this talk will be the following. Firstly, we'll present the string vibration and string barrier interaction models. Secondly, we'll explain the experimental measurement approach used in this paper. And finally, we compare the model outputs against the experimental data. So let's start with the string vibration modeling. The string is assumed to be ideal and lossy, given by the equation 1. Since the equation is linear, we can consider the wave equation shown here in the form 2 and add the losses separately. In our model, string vibration is obtained by directly exploiting the traveling wave solution, given here by expression 3, which states that the string shape is the superposition of traveling waves propagating in opposite directions. Here we have an example of the application of the traveling wave solution. As can be seen on the slide, we have selected a bell-shaped initial condition. Here the traveling wave moving to your right is shown with the green line, the traveling wave moving to the left is shown with the red line, and the resulting string shape is shown with the black thicker line. In order to add the string barrier interaction to the model, a purely kinematic approach, based also on the traveling wave solution, is used. Let's imagine a segment of a barrier, shown here with the gray-colored region, and the wave approaching it from the left. In order to guarantee that the string does not penetrate the barrier, a traveling wave moving to the right, meaning away from the barrier, is added and progressively modified in the manner showed on the slide. The above procedure can be written down as shown by expressions 4 and 5. Here x star denotes the spatial point where the string barrier contact is happening. Function b is the cross-section profile of the barrier segment shown above. At this point we stress that the function b can be selected arbitrarily. Let's take a look at the dynamic animation of the reflection discussed up to now. In order to simulate waves approaching a barrier from both sides, same procedure is used. Waves approaching from the left will be reflected to the right, and vice versa. In this simulation, we see a barrier with parabolic cross-section profile placed near the right edge of the string, and a bell-shaped pulse interacting with it. If one is interested only in a single point's vibration time series, it can be easily extracted as shown in this animation, where a point position at the midpoint of the string is extracted. Now let's continue with the second part of the presentation. In order to experimentally measure the string vibration, we use high-speed video chymographic approach based on the line scan camera imagery. Line scan cameras use a single light-sensitive pixel array to produce a video frame. These frames are then combined into a two-dimensional image, called chymograph. The figure on the top shows the string placement with respect to the line scan camera's point of view, shown here with the red markings. Figure on the bottom shows a typical chymograph of a vibrating string. In order to extract the vibration waveforms from the recorded chymographs, we use a digital image processing, which is based on the 1D correlation of chymograph frames, which are usually referred to as the lines. The red line in the top figure shows the 500th line of the chymograph. Formula 6 is the correlation used. Here P is the image depth value of a line and K is the correlation kernel. The shape of the kernel K is usually selected to be a bell-like curve. String position will correspond to the maximum of the correlation product S, as shown by the formula 7. Figure on the bottom shows the calibrated vibration time series that corresponds to the chymograph above. At this point we can proceed to the final part of the presentation, where we compare the presented model with the experimental measurements. In order to test the proposed model, a monochord equipped with a rigid barrier with a circular cross-section profile was built. We used a guitar nylon string with string gauge 15 and length of 66 centimeters. We excited the string with a triangular initial condition. This initial condition and the placement of the barrier are shown on the top graph. The bottom graph shows the measured string waveform recorded at the spatial point x sub m. Let's start this simulation and see how well the proposed model does. On this slide we have another vibration simulation of the same setup, taking place at a later time, between 95 and 120 milliseconds. As we can see, the model predicts the waveforms relatively accurately, given its simplicity. In the frequency domain, our model does not do so well. Here we see the spectrogram of the simulated time series, and here the spectrogram of the experimentally obtained time series. A detailed analysis of the reasons for the differences in the spectrograms is given in the paper. The most important reason is the lack of stiffness and thus dispersive wave propagation in our model. Notably, the spectrogram shown on this slide features an initial pitch glide, which is missing from the modeled result. Analysis of the time and frequency domain results showed that string barrier collision dynamics features two distinct vibration regimes. The initial short-lasting, violent regime, characterized by the high-energy collisions with the resulting pitch glide, and the more peaceful regime characterized by a relatively stable frequency spectrum. In conclusion, we presented experimental measurement results of the string vibration against a rigid barrier. We presented a relatively simple time-stepping model for string barrier collision modeling. The model was able to predict the vibration waveforms in the time domain relatively well, given the nonlinearity of the problem, but the frequency domain results were not so good. We discovered that the string barrier dynamics features two distinct vibration regimes. And finally, the video chymographic experimental measurement technique used in this study was proven to be highly reliable for our purposes. The method is highly suitable for small object and small displacement measurements, especially if high spatial and temporal data resolution is required. This concludes this presentation. Thank you for your attention.
Okay. Okay, so hello everyone.
Hello.
Hey.
Hello.
Let's see if we are we online yet? No? Yep. I guess we are online now. So hello everyone. I'm Federico Avanzini.
Hello.
Very nice meeting you all virtually. I thank you all the presenters for their presentations. We've had, I think, a very nice session with a lot of interconnections between these papers. They're all dealing with nonlinear aspects of musical acoustics and physical modeling. And they're also linked by the fact that all of them are funded by the Nordic SMC network, which is providing a lot of contributions to SMC. We have a quite lively audience, so we have quite a bunch of questions. Let's start with Rares with the first presentation. So we had questions from Sofia Dahl, which says, thank you for a nice presentation. I realize that the mapping to an interface is not the part of the work, but still I would be interested if you have any thoughts on which of these parameters that would be most important. So can you
Yes.
tell us more about this?
Yes. Firstly, thank you for the question, Sophia. In regards to which of the parameter, I presume from the physical model, the most important parameter, I would say, is the pressure amount, because with the pressure you can control the envelope and the attack of the sound, and that's an important aspect of brass instruments. And as said briefly in the presentation, it's controlled by the initial velocity of the key and some additional amount like aftertouch or an expression pedal. That being said, in terms of MIDI mapping, it depends very much on the type of interface that we're using. So if you have like a very normal keyboard and just an expression pedal, it's going to be a different type of interaction or variation as opposed to a rolly keyboard that I've shown briefly in the presentation at the beginning. So yeah.
Okay, thank you. So we also have right now an additional question came in from Antonio Roda, which asks if the VST plugin is available. The VST plugin is available to try.
The VST, unfortunately, not, because the VST plugin, this project was done in collaboration with Audio Modeling, so the plugin is not open source per se. Yeah.
Okay, that's understandable.
Yeah.
Let's switch to Silvin. We have quite a few questions for. So there were a couple of attendees, Chumur Erkut and Volmel Metspatis, that's the nickname, who asked about generally, I would say, more details about the collision potential part of the model. I don't know if you can add something about that.
Yeah, so as I said in the presentation, it's based on a model by Ducceschi and Bilbao of their 2019 DAFX paper. And it basically rewrites this potential in a different way so that we can discretize it explicitly. And basically the method that is used is a penalizing method. So what that means is that the two objects can actually penetrate, but once that happens, there's a strong opposing force, nonlinear opposing force to both of these objects colliding. So for more details on this quadratic potential, I'd like to refer you to their paper. Right, perfect. Again, on the model, David Rocchesso was asking about the friction model, the stick slip model used for the bow. Yeah, so we used a model that Stefan Bilbao proposed in his book, Numerical Sound Synthesis. And when I saw the question, I quickly made a drawing, so maybe you can see it's shaped like this. So it's an exponential function that is dependent on the relative velocity. So there. And yeah, so if the relative velocity is positive, then there's this curve that decides how much the force is then scaled. I actually don't know if this was mirrored in the Skype, but anyway. And a negative relative velocity would scale the force negatively. But if there's a very high relative velocity, you would only get a slip motion. So there's a very fine line for the bowing velocity in order to get sound. Yeah. Perfect. So it's a classic memoryless model mapping velocity to force. Yeah. Exactly. Yeah. And one more question about the model is from Federico Fontana about the pickup points that you chose from the body to get the final output sound. Yeah, so we kind of empirically did that. We have, as I mentioned in the demo, we have both the string, the mass, and the body that we can get sound from. And we kind of thought from the string you would have most sound closer to the ear, so higher up on the string. So I think we chose about like at 1/5 of the string. The details are in the paper. For that pickup point, and the body's pickup point, which is I think the most important part of his question, is directly where the bridge collides, because we think that also in the real instrument that is where the sound originates from that collision point. So we chose that as the output. And for the mass, it's of course just the state of the mass or the bridge. Yeah. Okay, and finally one question from Andrea Valle, who's asking something, if you have anything more to say about the actual comparisons between the synthesized sounds and the real ones. Right. We haven't done that yet. It would be very interesting to do some perceptual tests with recordings from the actual instrument and like the model itself. I think like a lot of work still needs to be done in parameter tuning, which is a pretty hard thing to do with these physical models and the amount of parameters that this model has. to make it sound as much like the real instrument as possible. But like informally, it was confirmed by us that there were many similarities between the tromba marina that we had at the university and the model that we made. Yeah.
Okay. We also have a last-minute question by Roberto Bresin, who's asking, zoom-out question. Why the tromba marina?
Well, physical models make it possible for instruments, rare instruments, or instruments that are just behind glass in museums, to be kind of resurrected again. So it would be interesting to find an instrument that almost no one knows and no one plays and almost doesn't exist, as opposed to a guitar, for example, or a violin, and try and model the interesting physics also in this case of the tromba marina, to make it available again to a wider audience. So that was kind of our goal, to resurrect this instrument, or at least towards the resurrection of this instrument. Yeah.
Right. Thank you very much. We have another question coming in, but maybe we should go back to the other papers and then go back to you if we have time.
Yeah.
I actually had one question for Dmitri. Very, very nice paper, and very interesting to see that as you said, such a simple, relatively simple kinematic model is able to account for such effect with such accuracy. I was wondering whether you can think of other features, additional features missing from the model, which could explain the discrepancies between the experimental data, the measured data, and the simulation from the model. One thing would be that I was thinking about is the collision itself. So you model the collisions as a completely inelastic phenomenon, where basically the displacement of the string is bounded to the surface of the obstacle of the. But I was wondering. I was wondering if you have considered other more sophisticated modeling approaches for the collision.
Well, yes, you could sort of introduce a force, a sort of an elastic force to it rather easily. So yeah, you could. So you're right. Yes, the modeling or the collision itself is the simplest way possible. It's not even physics; it's just kinematics, as you said. But yeah, you could define some sort of a potential that takes into account this amount that the string wants to penetrate, and just introduce a force that is proportional to that penetration, and that would be sort of an elastic collision. Did you hear me, or?
Yeah, absolutely.
Okay.
Yeah. I also had a question for Rares. I was wondering if you could add anything more about the finite difference scheme that you're using for discretizing the model, and if you have thought about looking more into that, because I read in the paper that you're using quite a big oversampling factor to have to get stable simulations that might be related to the fact that the difference scheme, finite difference scheme, is not optimal, or maybe in dealing with the nonlinear phenomenon involved in the simulations and so on and so forth.
Well, for the finite scheme, the work for the finite scheme is mostly focused on simulating the mass spring movement, and while normally a finite scheme for a mass spring would be pretty basic to simulate, due to the fact that we can modify elasticity and modify the attenuation due to the vortex-induced vibration. This introduces some energy and can destabilize the model in certain aspects. Like, for example, if we're using a normal sample rate, not oversampled, if we're going towards a higher frequency, that can destabilize the model during the vibration. In terms of improvement on that, well, I think there needs to be more study on it.
I haven't gone too much into that aspect. For the last 6 months, I focused mainly on the simulating of the tube resonator, because in the paper we're using a more simplified model. But it's definitely a point of future work of improvement in the next future.
Right, thank you. So maybe we have time to take also the last question to Silvin, which is by Marius Onofrey, who's asking whether you have control of choosing other pickup points in the VST, or maybe time varying pickup points.
That's interesting. I think for now we decided to have everything fixed, to be as close to the physical instrument as possible. But yeah, you're right. Like, physical models allow for like time varying anything. So it will be very interesting to kind of get like a pickup point that on the body goes around, or on the string that goes back and forth for like a kind of flanging or vibrato effect. I should say, though, that the body has been modeled to be very damped. So once you get away from this collision point, you will have way less sound. But yeah, that is something that we could investigate. Definitely. Yeah, thanks.
Okay, thank you. So I guess this concludes our question and answers session. I would like to thank again all the presenters for their presentations, and also the audience for their active participation. And I leave the mic to Andrea Valle.
Hello, hello all. Good morning, SMC community. I have just a short announcement. So now there is the piece by a very well-known composer, who is Alvin Curran. Sorry. The piece is Covidly Yours, Making Music with Anything. And after that, we present the piece Klingeln by Stefano Catena from 2019, that has not been broadcasted yesterday evening because of technical issues. Please note that this is a binaural piece, so wear your headphone. I'd like also to remind, on behalf of the music committees, that due to the COVID issue for this edition, we decided to stream the fixed media pieces that had been submitted for SMC. And as we have this opportunity of online participation, we thought it was important to let all the musicians in the C4 music submission category to participate, if they were willing to, of course, even if in this streaming format. So now music, and then we will be back with the next scientific session. Bye.
This is the new confusion. Thank you.